Ladies and gentlemen, welcome to the last talk today. The speaker is Shuo Zhang from Chinese Academy of Sciences. He is an expert in computational mathematics, particularly in finite element method, multi-level mixed element method, and structural method. Today, he is going to talk on structure-oriented paradigm for numerical schemes through exact complexes. Please join me in welcoming Professor Zhang.
So good afternoon. Thank you very much for this warm introduction. I hope to be an expert on the topics you mentioned. So I would like to first of all I would like to thank the organizing committee for this kind of invitation and provide me this opportunity to speak here. This is my first time to BIMSA, and I quite enjoy this beautiful center. And yes, it's quite a good place for research and for communication. And yeah, and I believe you will have the same opinion with me. So today I'm talking about some, this is the section of scientific computing, and I'm talking about some numerical schemes. And there are two issues of this. One is the structure-oriented paradigm, and another is about the exact complex. I would like to share some of my understanding and I think some results with you. Okay, this is the outline. I will begin with some preliminary introduction, and then we'll introduce in detail some. Okay, I will introduce the thought by this some fundamental examples and end with some conclusion. So, okay, what do I mean by this structure-oriented paradigm for numerical schemes? Let us come back to the very beginning of numerical scheme. We begin with just we consider this Poisson equation. This is or you can also call it the Laplacian equation. That is to say a partial u minus plus partial u equals to f in human table. And when we discretize it, we have many different choices. The first one is you know this the finite difference scheme. That is to say, we use this uij to be the for the approximation of u on a certain point, such denoted as xi and yg, and we can construct this scheme. And alternative is finite element scheme. The scheme is said to is okay. We have a subdivision of the domain, and we construct a space Vh for the approximation of this space on this subdivision, and we construct this discrete. We construct this discrete problem. So what's the difference? What's the difference between these two kinds of discretizations? Okay, we can see the basic difference that the origins of these two methods are different. Okay, the first one, the finite difference scheme, originates from the Newton's formulation of differential equation, and the second one is corresponding to the variational formulation of Lagrange. Okay, this is of course true, but I would like to say what we can get from these two different kinds of discretizations. For example, what can we get from this finite element more than a finite difference? A very basic observation is that by this finite element scheme, we can get a self-adjoint ellipticity. This ellipticity, this self-adjointness, is contained in the Poisson equation in its continuous form. And by this finite element discretization, we can get this property preserved by the discretization. I will not discuss too many details about this self-adjoint ellipticity, but I would like to say this preservation, this preservation of this ellipticity admit us to use the theory of functional analysis particularly the Banach closed range theorem to discuss, to analyze the finite element method. This is a key issue. This is very crucial in preserve the physical property of the original problem. So Professor Feng Kang, Professor Feng, okay, every Chinese computational mathematician knows this respected expert. He's a true expert of everything. At the very early age, Professor Feng observed this issue, and I just find in this paper his claim. He said that for a same physical law, there can be different representations, and these different representations can lead to different computational techniques to solve this same problem, but will produce different computational results. That is his survey, his observation survey. And then he said, a basic idea behind the design of numerical schemes is that they can preserve the properties of the original problem as much as possible. Now, this thing has been, has been widely accepted as a basic direction to design the scheme. And these two paragraphs can be surveyed as a Feng's principle. In Chinese, it's a Fengkang Yuanli or Fengkang Ding. And the basic insight of this Feng's principle is that for a same problem, there can be several different formulations. These formulations are mathematically they are equivalent, but computationally they can be not. This is a very basic insight. So I would like to emphasize that contained in his observation, contained in his insight, there can be some detailed perspective. That is to say, if two formulations are computationally equivalent, but they can be operationally not equivalent. I will provide some example later. And I just cite in an abstract way. Okay, for the computational point, the scheme design, the theoretical analysis, and the implementation can be different based on the special formulation of the problem, even though the formulations are equivalent in computational point. Even though. I will show you the example later. So if we want to design a good scheme, design a good a proper discretization scheme, we have to reformulate the problem to be a good one. The problem can be continuous or discrete. Even for a discrete system, it can be reformulated for ease. And if we want to reformulate the problem, we have to keep the equivalence. The problem should be equivalent to the original one, continuous level or discrete level. And also we reformulate the problem for some ease and correctness. The ease and correctness can be physical, mathematical, and computational. This is what we have to do. We are trying to construct some proper discretization. So now structure come out. What is structure? Why will I emphasize structure? That is to say, if we want to construct a good discretization, we have to discretize the whole theory, not just some of the equations. This is a very beginning point of this of the discussion here. And this sentence is not mine; it's contained in this book by Bobenko and Soris. They said not only they said this and we not only to apply a standard method to discretize. We have to decide what to preserve and what not necessarily. We have to determine these issues. And also we have to keep the equivalence and find some direction to reformulate the problem. This is what we are going to do. So if we have this opinion in our mind, we will consider the structure as an orientation. What is the structure? What is the structure? As we can see, structure is a pattern how the components of the systems are combined together. It's a pattern. It's a method. It's a way how the components, how the ingredients are combined together. They formulate the structure. When we come back to mechanics, we can see, okay, you go for some applied mechanics expert. He will say the three levels. The structure is the level between material and function. Materials, firstly, they formulate the structure, and then for this structure, it can be imposed by some function, and the structure is just the interlevel between the material and function. So I use this the structure to be the objective, objective we can work on to reformulate the problem to a proper formulation. And okay, and in this talk, I will focus on this structure of complex. So, okay, so what is the complex? What is complex? Complex is some concept we have been knowing. Okay, let us come back to the first year calculus, the first year of undergraduate calculus. That is to say, if you have a two-dimensional vector field, if this top is divergence free, then it has some string function. There is function phi such that tau equals to curl phi. Okay. This is a theory. This is in the field theory in your first year calculus. And okay, and if the domain has one hole, then there we, okay. I just consider two-dimensional domain. If the domain has one hole, then there is a function tau zero, denoted as tau zero, such that divergence tau zero is zero, and tau zero is orthogonal to the range of curve of any phi. And this is some harmonic function. So we can rewrite these facts in the language of complex. Okay. Complex is some concept in geometry, but I just use this meaning of a function and function space here. So we rewrite this as in the language of complex. That is to say, okay, the range R is the range here. The range of curve subset of the null space of D. This is what complex. This concept complex tells us. And another concept is exact. Exact means the range of curve is exactly equal to the null space of D. Then we said this is exact. And this formulation is exact complex, this identity. And the harmonic equation or harmonic form, that is some tau zero, it is divergence free, and tau zero is orthogonal to the curve, which means root phi tau zero is niches. And if these two are not equal to each other, then we can say that the quotient space, that is the null space minus the range space to be some cohomology. And okay, all these meaning are recorded in this notation, H1 curl into HD. And this means, okay, now we give some formal description. This V minus, V plus, and V are species. D minus, D plus are operators. And the combination of D minus and D plus is zero. That is to say, this is a structure of complex. And if the kernel of D plus is just the mean image, the range of D minus, then the closed form is exact. That is, and we can discretize this continuous complex to this discretized complex and to formulate something. Okay, this is I think this is the most famous example in numerical analysis of this continuous and discrete complex called the drum complex. Basically, okay. Anyway, basically this is the commutative diagram. This is the space for H1. This is the finite element space for H curve. This is for H div, and this for L2. Then this line is complex, and if the topology is simple, this is exact complex, exact discrete complex. And there is the interpolation here, and the interpolation and the complex commute. That is to say, from this direction and from this direction, identical. And the space H1 is by this finite element, H curl by this finite element, H du by this, and L2 by this. This is a Needlake element. This is a Ravel-Thomas element. This is the most famous example. And okay, currently the theory of complex, both continuous complex and discrete complex, have been a fundamental part of numerical analysis. I will not talk about too much details. I've only listed some brilliant drops in the bucket. And this paper is by Dog and Professor Dog Arnold and Taego Hu, who is the FAS prize of this conference, one of the prizes of this conference. And I will not talk about the complex, and I only show how to use complex to reformulate the method, the discretization. Okay, now I explain what it is. So in this talk, I will talk about how to use complex structure to reformulate the problem for ease, for correctness, for whatever you want. And if I have time, I will list these 3 examples. One example is that I use a discrete complex of primal space to get some neat analysis. I mean, the structure of complex can be used as a tool of theoretical analysis. And also, I show how the complex can be used for the for a scheme can be friendly implemented. And also, I will introduce the dual complex, show how to use the dual complex structure for natural discretization. And I will focus on fundamental model problems. But I think even for this fundamental model problem, it can find true applications, real applications, and these are the main references, and also I will mention some collaborated works with my friends. Okay, at this part I will talk about some optimal scheme for biharmonic equation. So, what is biharmonic equation? This problem is not as familiar to the community as Pozon, so let me introduce a little bit about that. This is biharmonic equation. That is Laplacian. This is Laplacian. Okay, circ combined with Laplacian square u equals to f, and with boundary condition u equals to 0, and its normal derivative equals to 0 to the boundary. This is the standard biharmonic equation. Okay, its most important application is to control the Kirchhoff simplate in 2D, in 2 dimension. But it can also find applications in many other real applications. And also, it's a model problem for high order space. The space the problem is very simple and it's very fundamental. So how to solve it? We just consider finite. Okay, I just focus on the finite element in this talk. How to construct finite element space? So Argyris, Johann Argyris, he presents H2 conforming finite element. defined as this. This finite element use here piecewise quintic fifth polynomial, fifth degree polynomial, piecewise fifth degree polynomial for the shape function, and use this continuity. That is the evaluation, the first order derivatives and the second order derivatives at every vertex, and also the normal derivatives at the edge. He used these continuities to construct H2 conforming finite element space with piecewise quintic polynomial. Agaris is very famous, you know. He's the fellow of Royal Society and a member of National Academy of Engineering of USD. So, and okay, and this finite element is constrained, is constructed for H2 problem. And recently, in 2024, maybe earlier, this finite element has been extended to HM problem in Rn by Hu Jun, Lin Ting, and Wu Qingyu, my friends. Okay, okay, the element is good, but the degree of polynomial is high. It uses fifth degree. So Morley made a contribution. He introduced this so-called Morley element. It uses piecewise quadratic polynomial P2 at every triangle, and the continuity, the vertex is the evaluation, and at the midpoint, the normal derivative. This, of course, this finite element is not conforming for H2 problem. It's not contained in H2, so it's not conforming. But it converges very well for the biharmonic equation. This is Morley. He's a fellow of many royal societies, royal blah 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 society. Okay, then Morley's element is okay. Let's come back. The Morley's element is in 2D and for H2 problem. And in actually in 2007, Professor Ming Wang and Professor Jin Chaoqu, they generalized Morley's element to this so-called Morley-Wang-Xu family. This family uses piecewise Pn to solve HM problem in Rn for any dimension, arbitrary dimension, arbitrary order of derivative, and it uses exactly the minimal piecewise polynomials, and not smaller than m. And this is now called Morley-Wang-Xu family. Okay, so what's now a consensus about the finite element? I will try to share my insight with you. Okay, Morley's element use piecewise quadratic is optimal. He use piecewise quadratic and gets the first order convergence, H1 convergence. And Agaris, he use quintic polynomial and get H order 4 convergence. So how about P3, P4? Can we use piecewise P3 to get H square convergence rate and P4 for H cubic convergence rate? This is, of course, this is a theoretical problem, but later we can see it's of practical importance. So this is the counterexample by Debord Devrand. It said if you use conforming finite element space, you cannot expect this convergence rate. He said if you construct the piecewise cubic finite element on this grid, globally it's H2, then the convergence rate will be one order lost. This is their discovery. So the point is that can we find the moderate optimality? Another issue is that if we use, now we can only use the non-conforming finite element method. That is to say, it's not a subspace of H2. We can only use a non-conforming one for the finite element. So okay, at the space H2 there is a famous Grace-Mas identity. That is to say, Laplacian U, Laplacian V, the inner product is equal to Hessian U, Hessian V, the inner product. This is very fundamental and okay. However, this identity does not hold for non-conforming one. For example, if we use Morley's element, this identity is not true, and this piecewise Laplacian inner product is not coercive. So what happened if we would like to solve this problem? For example, this sigma is not a constant. Then if we use Morley element to solve this equation, we will need this stabilization. So what's the issue of this stabilization? That is to say, the results can be sensitive to the stabilization, to the alpha, can be sensitive. So we would like to try to find some finite element so that this identity can be true. And this identity, if this identity is true, then this is a stronger result than this Miranda-Talenti estimate, which said that Hessian U can be bounded by Laplacian U. This identity means not only bounded but also equal. This is the stronger than this estimate. And this estimate can be very important, can be crucial for the computation of the second order non-divergence elliptic problem. And some of my friends teach my colleague Shuo Zhang, they have do many works on this. So what do? We use a piecewise cubic to solve these two questions. Okay, I do not think we are all familiar with the finite element. So I just go through some of these slides. So I can construct this finite element space this way, and this constructor is natural for a finite element space for H2 problem to be of H square order convergence accuracy. The point is that it's not a CLS finite element. I do not have too much time to explain the CLS finite element, and it's not. But the space has very locally supported basis functions. Every basis function can be supported on two neighbored cells or cells around a vertex. Every basis function falls into these two categories. So the point is that we do not have this finite element space to corresponding to a finite element. So how to analyze its approximation accuracy? Now we introduce this Fulton-Sully element. This is Fulton, but I cannot find any photo of Sully, so this should be Sully. They construct this non-conforming finite element for H1 problem. It uses piecewise quadratic polynomial and continuous at these two Gaussian points at every edge. Okay, now the story is here. We can prove that this space is just the space I defined 1 minute ago. And this is the space of Fulton-Sully space. There is a complex structure here between my space and the vector space of Fulton-Sully. The two are connected by this piecewise gradient and also this piecewise rotation. So what can we do? We have this complex structure. What can we do? Here, that is to say, this the gradient of this this is my space. Gradient B is just the kernel of Fortin-Sully of root. Then, if we concern the approximation error, we would like to find the best approximation of W in this space. That is to say, we will find the best approximation of gradient W in this gradient B3. Then it is transformed to the space of this Fortin-Sully. That is what happened. The key point is that for this space, there is a normal derivative. There is normal derivative at the edge. There is derivative at the edge. But for this space, there is no edge. There is no continuity restriction on the derivative. That is to say, the space is very flexible, and it is easy to find its structure and to use. That's the point. So by the aid of this space, by the aid of this kernel of root at via Fortin-Sully, we can prove this formulation. That is to say, phi, if phi is in this gradient space, then the best approximation of phi in this space is have a second order accuracy. That's it. So then the approximation is proved, and the convergence rate can be proved. That is to say, how we can use this complex structure to transfer the structure, unit structure of this space to the unit structure of this space of kernel of root at this space, and to analyze, to soften the problem. And further, we can show that for this space, its piecewise Laplacian inner product is equal to piecewise Hessian inner product. That is to say, since this space has this property, this space can be naturally used for problem of this formulation. Laplacian U, Laplacian V. Here is a coefficient which is not constant. And the performance is okay. Now let me show you what is here. What is the real problem that can be solved by this page? I just come back. I will come back to the slide later. Okay, we look into this equation. There is Laplacian here, and here, this is a coefficient which is not constant. So there is a Laplacian sigma Laplacian structure here. So this problem can be someone needs the property. So what's the problem? The problem originally is this Helmholtz transmission eigenvalue problem. The first one, the second line are two Helmholtz equations, and they are combined together to formulate an eigenvalue problem. And this problem can be used in I don't know, in inverse scattering problem and many others. And it is presented by Kirsch, by Cotton, and studied by Sacconi and others. So it can be formulated as this fourth order problem, and can be solved with this. And this is the co-work with my friend Jixia and Xingxia. And I can also use this space to solve this elasticity Mason eigenvalue problem. So that's it. I would like to emphasize that the discrete complex is not only a tool for theoretical analysis. Okay, let us come back to this discrete Griswas identity, which means this. The proof of this identity can come back to the proof to this property of this vector Fortin-Sully space, vector Fortin-Sully function. Can we come back to this? This formulation, this identity is always true for conforming one, for the subspace, for the functions in H1. But this identity is not true for general non-conforming finite element functions. Okay, but it holds for Fortin-Sully. That is to say, in some sense, these Fortin-Sully finite element functions are not far away from conforming finite element conforming spaces. This explains why the B3 can have this property. That is to say, this B3, the gradient B3 is contained in Fortin-Sully. That is to say, B3 itself is not far from H2. So this complex is not only a tool, it's not only a theoretical tool, but also something essence, some essence. That's what I want to say. Let me hurry. Okay, another example is the biharmonic equation, the order reduced scheme. So why will we study the order reduced scheme for biharmonic? Okay, let me come back to this model problem. As I said before, it can model the Kirchhoff plate, and it's a representative one. Why we use mixed formulation or order reduced formulation for H2? The point is that if we use order reduced formulation, we can just discretize the space H1 or other first order Sobolev spaces. If we discretize the first order Sobolev space, we do not care about the continuity of derivative. That's what. Then we will get big ease from here. But what is the issue? We just start from the classical formulation. That is, okay, U and W to be something like Laplacian U. Then we can have this system constructed on H1 spaces. The first issue is that the stability of this system is constructed on H1 and H negative 1 Laplacian. This is a complicated space, H negative 1 Laplacian. And also, if you discretize this system, then the stability can be constructed only by mesh-dependent nodes. Mesh-dependent. It will be the first issue is this. And another issue is that the equivalence. At the very beginning of this talk, we talk about the equivalence, but the equivalence is an issue for this formulation. We take this simply supported plate, for example. That means this plate is used U and Laplacian U for the boundary condition, for the boundary restriction. We use Morley element to calculate the 10 smallest eigenvalues. Every line is one eigenvalue. The 3 points are obtained at 3 meshes, and the 3 guys are almost the same, means that the eigenvalue have converged. We use this Morley element. And we use this classical mixed formulation to also to compute the 10 smallest eigenvalues. We use this blue line to denote that this eigenvalue can find its correspondence in Morley's calculation. And the red one cannot find their correspondence in Morley's results. So this red one are spurious. They are spurious mode. It's not good if the method does not converge, but it is even worse if it converges to wrong solution. It converges, but the solution is wrong. So, so we have to pay attention for the good mixed formulation. Okay, so what do we do? Let us firstly consider in 2D. In 2D, we just consider this formulation. That is to say, U is a solution of the equation, and we use phi to denote gradient U. Then the problem is reformulated as we find u and phi in h1 and h1 such that gradient u equals to phi and gradient phi gradient percent equals to fv. Here v and percent are gradient v equals to percent. We just formulate the problem as is expanded system. The point is how to impose gradient u equals to phi. Now, complex here. We have two complexes. One complex is that h2 gradient h1 root L2. They formulate a complex. This is called the Stokes complex. And another is this h1 gradient h root L2. They also formulate a complex. This is just the drum complex. Then we would like to impose the restriction that gradient v equals to percent. That is to say, percent belongs to gradient h1, the gradient and the percent are equal in gradient h1. This is a method to impose this identity. So how to impose this percent in gradient h1? Gradient percent in gradient h1 means, okay, we come back to this complex. Percent in gradient h1 means it's root free, means root percent equals to 0. That is root percent q, the inner product, equals to 0. Okay, that's all. So we just here, we introduce the restriction here, and we introduce a Lagrange multiplier here, and we can formulate this expanded system. This system is not that new. It can come back to Ravia's book and Arnaud de Brézy's paper. And then we can rewrite, we can subdivide this big system to several subsystems. The first line is Poisson, the second line is Stokes, and the last line is Poisson. And to solve. This formulation is equivalent to the original formulation, and we just use the standard finite element to solve. And okay, we just show you this picture. This line are computed by this new mixed formulation, and every eigenvalue can be corresponding to one of the Morris element, Morris structure. Morris result. And also we can use the method for transmission eigenvalues in I will omit the detail, and many others. These two papers has been published in University Problems. This is published this year. Okay, now the problem is how to study it in 3D. We can just repeat the procedure in 2D. We can repeat it. The logic is that gradient v equals to percent equivalent to percent belongs to gradient h1, the gradient equals to percent h1. So then we go curl percent equals to 0, and the curl percent inner product with tau equals to 0. Okay, where is tau? Tau should be this HD and the divergence free part. Okay, what is the difference? The difference is that in 3D, drums complex is one space longer than 2D. Drum complex is one space longer than 2D. So the point is that now we have to discretize this kernel space of HD. This is the point. We have to discretize it. How to discretize it? To discretize it is not as simple as L2. So maybe one more multiplier can help. But okay, so an alternative way is that we just look back into the method in 2D. In 2D, we have that gradient v. Okay, we are imposed gradient v equals to percent. Okay, we said gradient v minus percent and the gradient S, the inner product, and also this root, gradient V minus percent, and Q, the inner product, equals to 0. Here, S is in H1, the Q is in L2. This is what we have done in 2D. What is this term? This term means we can just get root here, that is the joint operator of root, denoted as root star. And what is Q? Q in L2. What is L2? L2 is root H1 root. So this line can be interpreted as this line. Now the point is, what is gradient H10 plus root star root H1? It is exactly this and this. This needs some background knowledge of the space, and I will not discuss too much here, but this hints us what is gradient V equals to percent. That is, gradient V equals to percent in gradient H10 plus H10. Let me repeat. V is in H10, percent is in H10, vector H10. Then gradient V equals to percent means gradient V equals to percent in this gradient H1 plus H1 in this summation space. This is what this formulation tells us. And what is this gradient H1 plus H1? It is exactly H root. And we can use this. This is the Riesz representation theorem. And based on this observation, we can find this expanded system. These are the restriction, and these are the Lagrange multiplier, and we can write it as this expanded system. The point is that we use this line, we use this space H curve, which is gradient H1 plus H1 for the Lagrange multiplier. Okay, so we can just generalize this point, this observation to general first order problems. There are many other first order problems, such as chord curve problem, first order Dewey equation, and this, and they can find applications in these branches. The only point I want to say here is how to define a first order problem. My definition of a first order problem is an elliptic problem on second order Sobolev spaces. This is my definition of first order problem. And okay, that is what we are studying. With this observation, we can formulate the space as U belong to H, the first order space, and derivative of U belongs to another first order space. And the point is that Y equals dV1 plus V2. Okay. So these slides are quite technical, and let me omit it. And we have examples not only biharmonic but also chord curve, and also gradient div, and many others. Let me omit. So I would like to introduce my interpretation of this stable decomposition, that H root equals to gradient H1 plus H1. This stable decomposition, decomposition, maybe stable summation, is very familiar to our community. So how to understand it? We still begin with these two complexes. And from these two complexes, we can get this observation. The first one is that gradient H1 is a subset of kernel of root. The second one is that H1, the root-free part of H1 square belong to this gradient H1. This is the second part. And the third observation is that the root, here, this root at the pre-image in H1, root is equivalent to gradient at the pre-image of root in H1. that is this in supercondition that is tau in this image of H1 vector H1, and this in supercondition is true. From this observation, from this two complex, we can observe that this root norm is an equivalent norm on this gradient H1 plus H1 squared, this space. This space itself is complete. Based on this observation, based on these two complex structures, we can show that root, the norm, is equivalent to the norm of to the intrinsic norm of this space. I still have so I can 5 minutes and 5 minutes. Okay. So the last part is the nature deep breeze method. Deep breeze is not a finite element method, but it is constructed on based on complex. Let me explain a little bit. Why we study natural deep breeze? What is natural deep breeze and why we study it? So basically, more and more works on the PDE, solving PDE use neural network. More and more works on that. So I said there are many popular approaches, including deep breeze and many others. One issue to use this neural network to solve the PDE is how to impose a boundary condition, how to impose a boundary condition into the system to discretize it. Generally, a penalty term is added into the loss function. Generally, is this. But the point is that, okay, we simply impose the boundary in the loss function. Then there are two parts. One is the bulk energy. Another is the penalty at the boundary. If we consider Poisson equation, the bulk energy is H1 stable, and the penalty at the boundary should be H half stable. But there is no way to impose a H half penalty at the boundary. There is no way. Otherwise, you will get a very dense formulation. So we will consider how to impose essential boundary condition without penalty. This is the motivation. Our method is to transfer essential problem to natural problems, and the natural problems, I mean with natural boundary conditions, these problems can be solved naturally by deep breeze. This is the key issue. How to do that? Okay, we begin with the Poisson equation, but the method can be generalized to wide applications. We can simply solve a Neumann boundary condition defined as this: Laplacian u tilde equals to f. Then Laplacian u tilde minus u, the residual, so the error. Laplacian the error is 0, and u tilde minus u equals to u tilde minus g on the boundary. This boundary term is known to us. Okay. What can we get? Because Laplacian u tilde minus u is 0, that is to say, this gradient u tilde minus u is divergence free. So naturally, this gradient u tilde minus u equals to some curl phi for some phi. So far, so trivial. And also, this curl phi equals to gradient blah blah. So it's root curl phi equals to 0. And also, curl phi dot t equals to partial t at u tilde minus g at the boundary. This is a boundary derivative of the trace of u tilde minus g. Is known to us. So this way we get a harmonic function equation of phi, and this is a natural boundary value problem. That's it. So we can solve phi use deep breeze and other method, and then we can gradient U tilde and curl phi to get gradient U. That's it. So what is the rule of complex? Here, there is not only a complex, but also a complex duality. So the complex is used here. Because this one is divergence free, so this one is equals to curl phi for some phi. This is the first. And also we can see there is a dual complex. This one is complex compact. Gradient is the adjoint of D. Root is the adjoint of curl. So this is a dual complex from right to left. And with this, we can see that the curl phi, solve this root-free equation. That is to say, root curl phi equals to 0, and it satisfies this harmonic equation, this natural boundary condition. So that's the whole story of this part, and not the whole story. There are many technical issues, but let me omit them. Oh, I just show one example. This is an exact solution. This is the U tilde. It's solved by the Neumann equation. This is the curl phi. This is the phi for the curl phi. We can see that most of phi is concentrated along near the boundary. So this phi record the boundary correction of the U tilde minus U. This is what phi do. This is boundary correction. Okay, so okay. I would like to emphasize this. This method do a primal to dual transformer, but it's from one elliptic problem to another elliptic problem. What can we do? The structure is this. U tilde minus U is gradient and gradient adjoint. At this harmonic operator, it's a harmonic. Phi is then it's a gradient star. I use these manners to denote the operator one space backward, one step backward, and this is gradient plus. That is gradient. The right operator of this is gradient. This is what the dual complex tells us. And there are two commutations here. One is a commutation of this adjoint operation, and the one step forward, one step backward. The operation, the two operations commute. Another is that the operator at the interior of the domain, and the trace operator, and the trace operator and the different operator along the boundary, the two commute. This is what the complex structure tells us, and they're generally true. Okay, some final conclusion that the complex structures can bridge different equivalent formulations for ease, and it can be used in many different ways. Okay, let me. Oh, they are my collaborators, and the first line are professors, and the last line are the students, and many of the students have been faculty now. Okay, thank you.
Okay, thanks for the very nice talk. Are there any questions or comments?
So I would like to understand better the discrete complex structure. So suppose for a specific problem, can I see any working finite element method can be somehow explained by the exact discrete complex? Is this a meaningful statement?
More and more complexes among finite element spaces have been discovered. So where is the destination? I don't know. Maybe some of them can be imposed in. Maybe some of them can be imposed in. Okay, your conjecture is that every space can be imposed in a complex.
Is that's my question? I don't know. I'm wondering.
Yeah.
Or maybe if the inverse statement is correct, like if you have some discrete space that can be written, with this exact discrete space, can we see that this finite dimensional space are good for the specific problem? This inverse statement.
Generally, if you can impose a finite element space in a discrete complex, that is to say, some more structure can be preserved.
Okay. Yeah.
So generally speaking, if you have this property, if you have this preservation, it can be expected to be better than not.
Okay. Okay. But so here the discrete complex, the exact discrete complex. I mean the operator you have, it's the original operator like the divergence curl, or you are considering some like divergence H curl H.
In this talk, every operation is local.
Okay.
Every operation is local. So I guess you mean divergence H is defined in a dual
globally.
Globally in a dual way. In this talk, everyone is local.
Okay, it's like at the nodes of the mesh, or like inside the elements of the mesh, right?
Yes, it's piecewise.
Piecewise. Okay.
Piecewise.
I see.
Thank you.
Okay, any other questions?
You mentioned several times that our method only works for elliptic problems, but what's the essential obstruction to generalize to other types of problems?
Okay. I do not think the problem works only for elliptic. I mean, the primal to dual. If you start from an elliptic Poisson equation, then you can transfer it to a dual formulation, mixed element formulation, right? So at this way, by this way, you can just transfer the essential boundary condition of elliptic formulation to a natural one for the mixed formulation, right? So this is a general way to transfer the essential boundary condition to the natural boundary condition. This is the general way. So I would like to say, in our work, we transfer the essential condition to the natural condition, but it's not from elliptic one to a mixed formulation. It's not to a saddle point, but it's from elliptic one to another elliptic one. By this elliptic one, you can use deep reason to solve it very friendly. This is the point. If you try to use a neural network method to solve a saddle point problem, the issue is that how to study something like in-soup condition and blah 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 blah. And so we still construct them in the elliptic formulation to avoid this danger.
So the obstruction is not the transforming step, but at the solving the dual problem step.
Sorry?
So you mean that the obstruction is not at the step where you transform it to a dual problem, but at the step of solving. Is that what you mean?
Yes. Yes. Thank you.
Okay. Any other question? Okay, let's thank speaker again.
Thank you.